So the next presentation is by Jonghyun Harry Lee. He's at the University of Hawaii, and his presentation is ML-based scalable data assimilation with hydrological applications.
Let me share the screen. Can you see my screen?
Yes.
So let me go to the presentation mode. Can you see the presentation mode?
Yes.
Okay. Thank you very much for the invitation. And I'm Harry Lee from Civil Environmental Engineering and Water Resources Research Center at the University of Hawaii. So today I'm talking about the data assimilation and inverse modeling approach in hydrological applications. Okay, so before I start the presentation, so here are the collaborators to help me to prevent this presentation. So from Stanford, Eric Darb, Peter Kitanis, Mustafa Burgami, and Dhruv Patel about the inverse modeling methodology, and Erdik, Beth Farding, and Tai Hesser for the data sets in the Riverine and coastal applications, and Hong Kyo-young from Sandia National Lab about the subsurface applications. Okay, so we observed a lot of recent progress in deep learning and that their application in geoscience and earth science. So this is basically from some kind of 4 factors that development in the another achievement in the big data, which is like remote sensing, geophysics, that you can actually observe the indirect data of the unknowns. And also you can actually have the numerical simulation and digital twins to generate a lot of data sets, input output sets to develop some kind of roadmap. And also software easily accessible, and also I would emphasize on the automatic differentiation, where you construct some kind of map, then you can actually get the derivative of the map, so that you can actually use the PD solver for using the deep learning approach, and also the hardware, GPU, FPGA, and other kind of things, and neural network, especially neural network, that you through the universal approximation that you can actually approximate any kind of a smooth continuous function using the neural network, and even over parameterization and other kind of things is not better than better, because we see that you have a lot of parameters. Then even if the training network is overfitted, then you can actually do generalize to some kind of applications. And there are a lot of things that can explain, and then so try to explain how this neural network can approximate functions quite well, and you can actually see. So I see that the remainder of the rest of the seminar, so a lot of the good talks will be lined up in applied mathematics. Okay, so our application. So basically, I'm from Hawaii, and then so it's Pacific Island, and all the hydrology is based on this coastal area, and the coastal area has a lot of population, and then require a lot of our resources or supply. Then there are certain 3 components really important in the hydrology applications, assuming that we know some kind of atmospheric inversing. So first thing is groundwater. There people are just dwell on the groundwater, and then can be predicted and solved by the advection diffusion, and then the groundwater flow equation, and also this one is quite interact in the saline groundwater, freshwater groundwater interaction, and also riverine. And river shallow water equation can be solved. This is the 1D equation. And coastal area, so you have to actually have the saline groundwater is governed by the wave equation, and the coastal and the offshore the physics, and then you can solve by the shallow water equation in the Bouchinic approximation is here and as a carbon equation. So the red the notation is usually the unknowns we try to estimate, because we are usually in the ground the numerical modeling of for the model has require a lot of perfect knowledge in their boundary condition and PD coefficient, and these parameters, so the conductivity, diffusion tensor, and the bathymetry in the river, and bathymetry in coastal area is some sort of the unknown parameters that are for the prediction. Okay, so inverse problem is like this. So we have the numerical model that assimilate, assuming that we have all the parameters, the pressure, the permeability, Riverine bathymetry, coastal bathymetry, and other things. And you can run the simulation expensively with the physics-based model or data-driven model, and you can get some kind of the observation or measurement or the quantity of interest. In reality, this is not possible because you have no imperfect technology, and the model itself is not perfect. So usually you have some kind of noisy measurement, it's just like pressure, concentration, and wave characteristics, riverine velocity. Then you try to use this kind of the observation, try to estimate this coefficient. And this once you have this coefficient, and you can actually do some kind of prediction and forecast for the future purposes. The problem of this inverse problem, why the food problem? So from the solving PD coefficient to the PD output is well posed, where the solution is exist, and then solution is the determinate the exist and the unique. But the problem is here, the inverse problem is ill posed, where the solution may not exist, or if exists, this is not unique, and also the some sort of error in the measurements or numerical modeling or PD, our current knowledge of the state of the system can be very affect the output quantity, and is very sensitive to noise. So because of this nature of the inverse problem, we need to account some kind of best estimate of the unknown coefficient and variables, and also need to account the uncertainty in the model and data. Okay, so what may actually think about the using the neural network and other kind of the machine learning technology? So we basically, in the supervised learning, you just have the input and output pairs, and then you try to construct some kind of folder map on data-driven map. And maybe you can use some kind of construct a direct inverse map. So using the output and try to with the paired with the input, and you can construct inverse modeling or inverse map. Then you can use the like in the neural network approximate this inverse map and then doing the inversion. So we actually done before this kind of things, and the problem issue is that how you can actually quantify the uncertainty in this case. So constructing inverse map is okay, but it's deterministic. You may actually use some sort of the traditional statistical techniques like parametric bootstrapping or Bayesian drawal, but it requires additional hyperparameter estimation, and also it has some kind of it does not it lacks of the generalization capability, and based on this kind of the input output pairs, so this is limited. So more the traditional and the classical and also the widely known inverse modeling framework is basically you are using the Bayesian framework. So in that case, so you have the prior information, prior PDF is proposed to regularize the solution of the inverse problem, and so then you use the measurement to update prior, and if it is data assimilation, you just sequentially update the posterior PDF or your unknowns. And if it is inverse problem, you have only one batch inversion, so that you construct the posterior map and estimate, and then there are uncertainty. And method is stable because you actually introduce some sort of prior information and well posed, and regardless of amount of quality and other measurements. And so here is the common approach, and you use the hierarchical Bayesian and the deterministic approach. And this you can actually look into some details in our recent paper in Journal of Hydrology about recent advance in the data assimilation, inverse modeling, and how you can actually accelerate this one without the machine learning technology. Okay, so what is the formulation? So as I mentioned before, instead of constructing the direct inverse map, so what we can actually do is just following the Bayesian the inversion approach, Bayesian framework, and so that we have two terms that we just try to minimize the feeding or the data misfit, and also you just try to have your estimate is close to the prior. Then if we try to find the one best estimate in this case, so deterministic case, and you can actually use the Gauss-Newton iteration, a Gauss-Newton approach. Basically, you are just minimizing or maximizing this posterior and find the best model. And usually, if it is Gaussian, it's basically the mode and the conditional mean is the same. So you are using this kind of the iterative approach and try to find the best estimate. And if you have best estimate, you can actually linearize around this best estimate to get the posterior covariance matrix or covariance of the second moment of uncertainty. So using the Kramer-Rao the low bound, so this is basically low bound of the uncertainty of your estimate. Okay, so what is the issue with this traditional approach? It's basically, so it is computationally expensive. If we just only use the finding on one mode, and you are just finding the estimation of PD coefficient, like the permeability in the groundwater equation or petroleum engineering or bathymetry in the Riverine setting. So it usually becomes, number of unknowns, it becomes like millions or something like that. And observation can be like, order of the 10,000 or so more using the satellite information and then geophysics. So in this case, the number of the numerical model runs requires like, order of the, so if we use the very efficient adjoint state method, it will require about the order of the number of observations times the iterations. And so also we have the, if we assume that the deterministic approach with the Gaussian process, Gaussian prior, then it requires invert and multiply matrix of the largest size, like million by million. So what people usually do is to reduce the models and of the full model. And also sometimes we can actually do the projection onto the lower dimensional space of the covariance matrix, which is basically, so you're looking at the prior information and then prior, so reduce the space of prior and then just regularize the solution onto this prior so that you can actually get the accelerated solution by approximating Jacobian vector product. So here's the kind of linear projection-based inversion method. And then if you use the FFT or the hierarchical matrix and fast multi method, and you can use the, so matrix multiplication can be reduced to the order n cost, where n is the number of the degree of freedom, so like a million, instead of the million square or million cubic. And so you're projecting onto the small dimensional space of the prior, then you can solve the problem. And even within this problem, you can construct the sensitivity Jacobian matrix by just perturbing this one onto the this prior mode prior directions. Okay, so here are some kind of the example that we used this kind of linear projection method. And so this is the coastal bathymetry estimation problem where in the North Carolina. So where you observe the real time using the drone to get to know the wave speed from the near shore, so that you can actually construct get the wave speed from the camera that you can actually observe from the UAS. And you contrast this, and then from the frequency domain, you can actually get the signal from the other, and then you can get the wave celerity, and also structure for motion can actually allow us to get the inland elevation. So in the right plot and the top plot is direct survey and interpolate and followed by the interpolation, and this is truth. And then so using the way the celerity and inland elevation, and you can actually get the quite good bathymetry over the water bottom of this coastal area that can be served as the boundary condition of your groundwater model. So this is quite good. And then if you just project this one onto the linear prior space, then you only need about 100 or a few hundred numerical runs for the wave simulation. Okay. Other thing is Riverine bathymetry example that where you are just having this kind of the river setting. So 1 mile reach of the Savannah River in Georgia, and you have the direct survey from this Savannah River, and then there's a left plot is basically the bottom elevation of the Savannah River during this survey campaign, and using the velocity and velocity measurement of surface and the shallow water equation, you can actually invert and data assimilate this one, and you can estimate the bottom topography or elevation or bathymetry of this one. And then using these kind of things within the projection-based method, and then also before mentioned the fast linear algebra products, then you can actually achieve this one within within a few hundred shallow water model, and also within a reasonable file time for the guidance of the some logistic application or defense applications. So this is the linear approach where we use the traditional way, But how about this one? So basically, how about using the machine learning or neural network type techniques? So previous approach shows great success, but it remains limited by the linear projection. Also, it is using Gaussian estimation, meaning that if you have a sparse data, so you probably get some kind of smooth version of the true spatial process. So you may actually use some kind of neural network and also generative model, deep generative model, like the variational autoencoder against to this kind of leverage nonlinear projection operators. So basically, this has two benefits. One is you can actually so accelerate all kinds of things, and also looking at some kind of nonlinear projection, which may reduce the number of dimensions in the latent space. Second, so previously this is only for the Gaussian estimation for certain parameters. Now we actually use some sort of the data-driven priors, where you can actually have a lot of the samples, and you can generate with statistics, multi-point statistics, and other things. So for the spatial process, use this kind of information to construct your own customized prior, so that it can probably achieve some sort of more accurate, much more accurate estimation, and also the reduced uncertainty, and also it component is the nonlinear reduced order model construction. So for the model, so from the coefficient to the model output, so you can actually there is some sort of examples we used before. So one is the digital twins. So basically, there are quite limited amount of field of data set in some certain applications, so that you can actually augment this data just supplement data from the numerical models. And of course, numerical model has some sort of errors, and then so that this will not actually reduce the uncertainty in the real data. But there are also other prospecting, probably promising area, like you are using the digital twins. So in this case, this is the wave model in nearshore. So, and this is not only just solving for the model with the PDs, but also there's some kind of sunlight effect, and then light tracing and other things, so that it is actually just provide the realistic images of the numerical simulation, so that you just take the input and output pairs into the format, and then can be directly applicable to the real data sets. And another area in the ROM is basically physics-informed neural network. So basically, I saw that Dr. Jonghyun Harry will actually present next days. So you can actually use the incorporate. So instead of just using the only pure data approach, driven approach, you can incorporate the physics or PD information as a loss function, so that you can actually reduce you can actually reduce the error in the data-driven approach, and you can compensate all these some kind of advantage of the numerical solvers that is managed over decades. So, but probably the issue with pins, when I use and from my experience, basically this is hard to optimize and hard to train the data, and so it's not easy to generalize to the new domain other things. So we heard a lot of zero training, one-shot training, and other kind of things to generalize. But once you just develop one model with the large number of the GPUs, then if you just change the domain or just some kind of boundary condition, other things, and probably the previous training model is useless, and then so you make actually a fine-tuning or transfer learning to do this one for another domain. So this is probably can be some active area of study. So previously, I talked about the prior space and the linear projection. How we can actually achieve the prior space in nonlinear for the nonlinear projection. So basically, you can actually use the autoencoder, and then with some kind of bottleneck in the middle from input to output, so that you can actually construct this one. And this bottleneck can be used for the small dimension of the latent space, and then you can use this small dimension space as a decoder part for the fast prediction of the outputs, and then also only you can focus on the small dimension to estimate the parameters. With the assumption that your latent space is well conditioned and without any kind of ensemble collapse or just latent space collapse, and so that's the assumption. Okay, and also you can actually use the GANs. So GAN is basically you are just achieving the equilibrium between the generative model and the discriminative model, and you can actually use this one. And then we saw that especially in the geoscience application, and it is working quite well. And even simulation with this kind of generation is quite feasible in many. It's a promising results. Okay. So variation autoencoder, and let's say some sort of the bathymetry estimation problem, you can actually have construct the bathymetry to bathymetry to self-supervised learning to get the latent space with variation autoencoder. And we prefer variation autoencoder because it has the latent space distribution is forced to have the identical IID distribution of the Gaussian. Okay, and this kind of the encoder-based inversion approach is quite useful, whether that so that you can actually encode any kind of the realizations and then numerical models. Here, just example is basically you can use the different Gaussian process with the anisotropy and then the regularity or smoothness of from the Gaussian to exponential or any kind of mathematical model with the different parameters. You can learn this one just one set of the encoder. So using this kind of map from the latent space to observation, you can actually construct the reduced order model, and that's the advantage, additional advantage from the this kind of approach. So here, our application is basically try to estimate bathymetry from the velocity, and then the fourth model is bathymetry. Given the bathymetry, you get the velocity. And you also have the additional layer of the bathymetry self-supervised estimation, so that the latent space can get the information of input and output features, so that you can actually construct the more informations there, and also the accelerate the for the model. So you probably add this here as a constraint of the physics informed neural network and governing PDs. Okay. And so, and with this kind of settings, you can actually modify the inversion strategy. So like Gauss-Newton method. And so here now, so you can actually using the construct Jacobian or sensitivity or gradient of the forward operator using the automatic differentiation. And so that you can actually update this kind of the estimation variable and bathymetry here or permeability and other things easily and in a second once you train your autoencoder. And here are some kind of examples with the different types of bathymetry here. So so this is synthetic bathymetry for our science, and using the this kind of example, 3 example bathymetry, and run the full model the shallow water equation, you get the surface velocity. And using the velocity with our approach, and then resolve the model for the shallow water equation, and then latent dimension inversion. So we got the some kind of good results. So the rightmost column is basically the inversion based on the Gaussian estimation, and you can clearly see. So root mean square error is quite smaller than the linear projection based method, because so given this kind of the same number of dimensions, it encode the nonlinear projection approaches encode more information and more basis, so that it actually reduce the errors in the inversion. And so this this plot is basically initial random the latent space variable, and then once you estimate this one, is very close to the distribution of the latent space variable is close to the z value. Okay, we just tried the sparse measurement, and it's still, because of the quite strong information from the prior, we get the quite good results. And ongoing work is basically you can so instead of using the map estimation, you can actually characterize full posterior PDF. And what we can do is using this kind of the reduced order model and the very fast solver, so you can actually sample and to get the entire the high order moment of your posterior PDF. But so in this case, we probably used some kind of local information. So from the gradient-based method, and you may have the local information like Hessian matrix as some sort of the proposed density of the MCMC type of method, and you can use the preconditioned Hessian preconditioned Langevin method to fast accelerate with Monte Carlo method to do that. So this is some sort of the preliminary result, and showing that so in this kind of the method, it is quite close to the map estimate, and standard deviation is a little bit larger because of this previous map estimate is based on the linearized uncertainty, so that this is probably low bound. So, and with that Metropolis Hastings method and then this Stochastic Newton method, it can accelerate the this kind of MCMC method convergence, so that it only requires our recent results shows that like few thousand to the 10,000 the model evaluation, reduced model evaluation is enough to converge to and then fully characterize a posterior PDF. Okay, so conclusions. So supervised variational autoencoder and deep generative model offers great promise to build accurate ROMs and the reduced order model and great flexibility and accuracy. And combined with the Bayesian formulation, it actually can allow us to do the rapid stochastic inverse modeling and data simulation. So we need the offline training of the variational encoder or GANs. So I prefer variational encoder because it is quite cheap to get the good result for now. So for the preliminary analysis, probably GAN, which require about 1,000 and 10,000 epochs, maybe used for some kind of the complex distribution. And then once you have this kind of the nonlinear projector and also the reduced order model, then you can actually perform the rapid online predictions. And also the additional advantage is data-driven prior improves the accuracy compared to the standard Gaussian priors. Okay, so this is the end of my presentation. Before I end, so I want to just advertise this the AAAI Science Guide, the symposium in fall. So basically, this is led by one of the organizers here, the Vipin Kumar, and so this is we have a lot of the good speakers in lineup in last year, and we also get the call for the papers. So I like to encourage you to participate in this conference. Okay, and thank you. And any questions?
Yeah, thank you, Harry. Yeah, we're close to or past the end actually, but we do have one question, and that is, what was subsurface salt water intrusion included in the model and observations?
I'll say that again. Subsurface.
Yeah, but subsurface salt water intrusion included.
Yeah, you can actually use this. Basically, it's totally depend on the domain of your interest. If you are just looking the coastal aquifer, yeah, definitely you can use that. But that will require a lot of the PD solvers. So you need to like the density-driven flow formulation in the your reduced order model, and you can actually achieve these kind of things well as a constraint.
All right, thank you.